and hello everyone to this entry of the Radiation Heat Transfer Learning Journal. In the last video, we were discussing some sort of spectral emissivity and absorptivity, and we have gone through lots of definitions about intensity, about absorptivity, etc., etc. And why have we been doing all this? Now, this was always a prelude to having a radiation. We want to quantify or calculate radiative heat transfer between surfaces. So there are a few simple cases. Let's say you have an arbitrary surface A1 and some arbitrary surface A2, and let's say both of them are black bodies. So that means, well, based on our last definitions of emissivity and absorptivity, the absorptivity is 1 and the emissivity is also 1. And yeah, for most calculations, you can assume both of these are pretty much the same thing. Absorptivity is emissivity for all our intents and purposes. But the thing is, okay, for this surface-to-surface heat transfer, emissivity and absorptivity don't really play that much of a role yet, since they're always 1. So the more important case is if you have, let's say, two surfaces where the heat transfer between them occurs, and both of them are not black. This means to say they are either some kind of a steel or shiny surfaces or something like that. Okay, so these are non-black non-black surfaces, non-black. So the absorptivity and emissivity here will not be equals to 1. Sometimes they are depending on spectrum, as you can see. As you can see over here, they will be dependent on the spectrum. They'll be dependent on angle and temperature, etc., etc. Right? So yeah, so we have we have heat transfer between black surfaces. Okay, so I'm just gonna select this to copy and paste. Okay, we have case 1, black surfaces, and let's minimize this. And case 2, non-black surfaces, and there you go. Alright, non-black. And a special subset of these, case, let's say 2.1, we'll have this thing called gray surfaces. It's either GRAY or GREY, but they mean the same thing. Okay, so what are gray surfaces? There's one special case of a non-black. I'll just paste it here, and I'll just delete this bit. Now I'll just put gray. Gray surfaces. So what are gray surfaces? It means that the spectrum is not important. Okay, so that's our case 2.1. So I mean, for non-black surfaces in general, if you want to talk about heat transfer between them, it will be pretty complicated, especially when spectral dependence comes in. So with gray surfaces, it is much simpler. And if we add another simplification is gray diffuse surfaces. Okay, gray diffuse. Okay, what is diffuse? Diffuse means okay, let's write diffuse just to recap if you have not already known what this is. This is direction independent. Okay, let me write that properly. Independent. Okay, so let's do direction independent. Okay, this is gray diffuse surfaces. Okay, so that's probably something that's much more practically calculatable by hand as compared to this and this, because this one will not be diffuse, therefore you will have to take angles into account, and that will be pretty complicated. Okay, so we can start with the most simple case first, black surfaces, and when we want to extend it to, let's say, a gray diffuse surface, we can bring in the emissivity and absorptivity in. So we start with simple, and we go with, we add levels of complication, which in this case is a gray diffuse surface where, okay, the emissivity and absorptivity is not 1. So that's why we spent all that time in the last 7 videos talking about emissivity and absorptivity, intensity, etc., etc. So let's talk between two black surfaces. So the simplest case we want to consider is between, let's say, two black surfaces. Okay. All right. So let's say we have two arbitrary black surfaces. So yes, if you have two arbitrary black surfaces with let's say A1 going to some funny shape of A2, what's the heat transfer between them if there are two temperatures, for example? Okay, so first thing first, between two black surfaces, we need to consider the intensity. So let's say the first surface A1 is at some temperature T1. So we have to consider the IB lambda. Okay, this is the black body, what do you call that? Intensity. So what is it a function of? So we have to kind of go back to what we are talking about. All right. So IB lambda, it is equals to, you know, we need to consider this temperature, okay, and we need to consider the fact that it is altered by angles. So you can see EB lambda is something like this. Okay, so if you remember Lambert's cosine law, oh yes, Lambert's law is here. Okay, so okay, you have the relation between the spectral emissive power and then the intensity as well. So we'll put it here. So we have to note that IB lambda is this much. Okay. And yes, where is EB lambda? EB lambda is based on this. You have this based on, yeah, remember quantum physics. It will give you that expression. So we have EB lambda, equals to this. So IB lambda is equals to whatever this expression is, divided by 1 over cosine of theta. So there is some angle dependence there. All right. So that's how we find that. And of course, if we are doing, since it's a black body, it does not really matter, right? And we remember the how we integrated it to get sigma t to the 4th. Yeah, so it's sigma t to the 4th because since both of these are really black surfaces, they will just absorb and emit all the radiation coming in. So frequency doesn't really matter. So if we take a look earlier, okay, take a look earlier, emissive power, okay, we got something sigma t to the 4th, which is this little thing here. So EB, if we integrate, that happens if we integrate EB lambda across the whole spectrum. So let me just copy these things down to take note. In total, since spectrum is not important, we use, okay, I'll paste this here, and of course we use the entire spectrum, and this will be over here, sigma t to the fourth, right? Alright, so sigma t to the fourth, and this is integrating across all angles, and there's nothing to do with the directionality of it. So we can just say that IB equals to n squared sigma t to the fourth. So this is after integrating across all spectra, 1 over cosine theta, right? 1 over cosine theta, because this is Lambert's law. So okay, so that's part 1. That's the power per unit. So that's the power per unit. Per unit angle, per unit area. Okay, power per unit solid angle per unit normal area. All right. So this is what the black body intensity kind of looks like. Now, of course, so if we have an expression for the power per unit solid angle per unit normal area, we'll have something that looks like this. Okay. So now the tricky bit is of course to incorporate all the solid angle, area, everything into this expression. So what is the first thing we need to do? Okay, we want to consider the geometric effects of heat transfer. Okay, we want to consider the geometric effects on radiation heat transfer. All right, so what's the next step? So we need to consider something called view factors, and that will take care of all this solid angle, orientation, etc., etc. And okay, we will just go through some revision on that, since we have already talked about a little bit of directional dependence and directional dependence. So if we were to consider directional dependence, at least the shape of the surfaces, in this case, we will have to consider view factors, and we'll go more in depth. Okay, we'll go more in depth in the next video. So thanks for watching. Hopefully this gives you a good overview of why we need to consider view factors, why we need to consider absorptivity, etc., etc., especially when it comes to radiation heat transfer between two surfaces like these. Thanks for watching. I'll see you guys next time. Bye bye.